Hi everyone, I hope everyone hear me here. Okay, so I'm pleased to be here with you today to share with you some of my experience in Kaggle during several years. So the title is called Is Easy, so it's quite different from other talks where it was more technical about how to win competitions. Here I will keep it rather simple and I will talk about what I was doing before and what I started doing to improve myself. So I will start by giving some general advices that everyone should follow, and I will talk about some technical stuff, mainly about how to improve or to check for improvements in your models. And then I will talk quickly about some case studies and see that you will see that getting a gold medal is not most of the time, it's not that difficult. So starting with the advices, first advice, positive mind. If others can do it, you can also do it. And that is how I started. When I started Kaggle, I said, if those people can do it, I can do it. And I compete a lot and I managed to become a grandmaster. Second advice, understand the problem and try to find new ideas. Never start fine-tuning your model during the first week while you are still doing some feature engineering steps, you are still looking for a good architectures. You will just waste most of your time doing fine-tuning. Spend this time trying different approaches, different architectures to come up with different models for your final ensemble. Third advice, don't use kernels when you start a computation. You will mostly end up using a slight variation of that kernel. So don't look at kernels when you start. Try doing that data analysis by yourself. Try to come up with your own models, with your own feature engineering. You will end up with models that are different from those that you will find on Kaggle. Later on, you can use ideas, you can borrow ideas from Kaggle kernels to help your model improve even better. If you have the chance to work in teams, don't share anything except some important insights. So when I work in team with my teammates, we don't share the architectures of our models. We don't share the features that we create. We only share important insights that we find by doing the analysis of the data. If something doesn't work, don't stick to it. You will mainly waste your time. Find a different approach, try different modeling approaches to your problem. You will end up with different solutions that may help you. Another advice is you should always keep it simple. We saw previously in different competitions some awesome solutions that use hundreds of models with stacking, and as beginners or even at some advanced levels, you may say that I will never be able to do something like this. Stacking is very an advanced topic. So try to make simple models. Simple models will also work and help you to get a gold medal. Don't underestimate the power of neural networks. Even on tabular data, mostly on tabular data, people try to use only gradient boosting decision trees because they are so powerful. Neural networks can be as good as gradient boosting decision trees if you are able to come up with good architectures. And it will also help you in your final ensemble if you are working with two models, gradient boosting decision trees and neural nets. Another point is transfer ideas. That's how I call it. Is try to work on different fields. Do images, NLP, time series, tabular classification, regression. Try to work on as many different topics as possible. Ideas that you may use in images, for example, can be used on tabular data if you know how to model your problem in order to use such ideas. And the last idea, and the last point is thinking outside of the box. don't try to do what other people do, because you will end up with the same solution and you will end up with the same ranking. Try to do things that people don't think about. Try new stuff, new ideas. Most of the time there will be crazy ideas that may not work, but you have to try them. And if one of those ideas work, it will get you the gold medal. So check in for improvement. I will start talking about feature importance and how to assess the importance of features. So one thing that I have noticed among Kagglers is that they are always trying to eliminate features, looking for the low-ranked features, trying to eliminate them in order to improve the performance of the model and to make it faster to train. So I never do that when I start a competition. When I say I never do that, it's during the first modeling approach, but later on you have to do it. So why I don't use it? I don't eliminate ranked features when I start, because you may have correlated features that may explain the low ranking of some features. When we will do feature engineering, new features that you will end up coming with may have some good interactions with the low ranked features, and you will see an increase in their importance. And also the ranking of the features is dependent on the complexity of the models. Some low ranked features may become really important if you increase the complexity, or if you decrease the complexity, some high important features may decrease. So here is an example using the Titanic example. So on the left, you can see the original raw features, and on the right, I just added a new feature that I call noise feature that I made from a normal distribution. And as you can see, I made a grid search trying to find the best parameters for the two models, and you can see here that the noisy feature is ranked third, which doesn't make sense. This is just random noise. So if you start looking at the low-ranked features, you will try to eliminate some of those features and you will completely forget about the noisy feature. So this is something I have noticed when I was working on the first Zillow competition. I made up hundreds of features and I tried to use the noise feature trick, which is just made a noisy feature and see the ranking. And if anything is ranked below the noisy feature, it just means that it's just noise. You can eliminate this. But it happens that in practice it doesn't work. And my noisy feature, even though I have hundreds of features, was always ranked in the top 5 features. So don't look at the low ranked features, but start looking at those that are ranked very, very high. Your model is probably overfitting on some noisy features, and by eliminating those features first, the low-ranked features may become more important because your model will try to use them instead of using the noisy features. So the main focus is to detect the overfitting features. You have two choices. You remove them if it helps your cross-validation, and if it hurts your cross-validation, then just try to apply some transformation on those features to have a better generalization. So the second part of checking the improvements is about feature engineering. And this is quite tricky to find what feature is working or not. So when you come up with a new feature and you want to check if this feature is helpful in your model or not. Well, if you see a very important increase in your score, you know for sure that the feature is helpful. But most of the time, the features just give you some little improvements, some little increase or maybe decrease in your cross-validation score. So how will you assess that, for example, the score change happens from using this feature, or is it just from some random seed that you are using into your model? So first approach that you can use is doing bugging. So what is bugging? Is just use the same model with different seeds and try to average the predictions out of those models and see the final your final cross-validation score. So instead of using a 5-fold cross-validation, this will allow you to use just one random seed. It's just one model. I prefer using 3 bags of 3 folds. It's almost as fast as doing a 5 cross-validation because you have less training data and it's just 3 folds instead of 5 folds, so it's almost as fast. But it allows me to use 3 different models with 3 different seeds. And by blending those models, I somehow get rid of the randomness of, so my final score is not really dependent of the seed that have been used in my model. And I can be quite sure that the improvements that I see is not coming from randomness, but really from the improvement. So this is one way to do it. The second way, and this is how I do things when I do feature engineering, is I never use or I never test only one feature at once. I create what I call, I will be back to this slide later. I always do what I call a bunch of features. So I create, let's say for example, 5 features. And instead of trying those features one by one, I try the full bunch of features at once. And if improvement there is, it will be not a very small improvement, but rather a quite important improvement. And this works very, very well. So why does it work so well? Well, let's imagine that you have 2 features. Feature 1, which is just a mean computed on some feature X, grouped by feature Y, and some other feature 2 that use the feature 1, but you just remove the mean from your feature X. You may end up, if you try those features one by one, you may end up by not seeing any improvement in your model. But using them both in your model, you may come up with some interesting improvements. Why? Because those 2 features are quite related between them. One is the mean of the group, and the other is just the difference of the feature X to this mean. And maybe this feature 2 is not working quite good by itself unless it has some kind of interaction with the mean of the group. So by creating a bunch of features, you are allowing for more interactions than trying feature by feature. And when you are done with this bunch of features, you make, for example, 5 features, and you see improvements. At that point, you can start looking if you have any overfitting features, and you can sometimes, what I do is starting doing feature selection during my bunch of feature creation. So I create like 10 features, I see improvements, I check for overfitting features, I remove them and see if all the features are useful. So some features may not be useful into this bunch, so I just remove it. Okay. One of the most powerful features that I have found so far, and it almost always works, is this feature, this kind of features. You group by some feature Y and you compute some statistics using another feature. And then you just remove that mean from the original row of feature. So you apply this on categorical features. You can also do it on discrete numerical features. And you can also apply it on continuous features by doing some discretization just before. Also, tabular data can have spatial and temporal information in them, so you may group by different features with different granularities. You may also derive your own granularities from to make your group I working. So we, in the 2 Sigma competition, we end up in the second place just by using those kind of features. So we have some technical indicators and some fundamental indicators, and we did this on some features, and our group by our Y feature was the day. So for each day, we just compute the mean and look at the deviation of each sample, of each observation to the mean at that given day. And we end up with different models that we blend together, and that was enough to win the competition, just with those kind of features. The third part for improvement is about the outliers. So here I'm going to talk about outliers in the targets that you are trying to predict. So outliers can be due to different reasons. So for example, in the home pricing, you may contain some typos. Maybe you have some underpriced sales because sales happened between family members, or maybe there was some fraud that happened. So you have something that you cannot predict because it's underpriced, or maybe you have something overpriced, some sales that big houses on some big island, but you have very few samples of them, so you cannot find some interesting patterns. You have not enough samples to learn anything interesting from them. So how to deal with this kind of outliers? So during the training phase, you can start by keeping the outliers and have some kind of baseline score. Then you can apply some transformation on the target and see if there is any improvement. Later on, you can do what we call winsorization. So winsorization, I will talk about it later. This is the second thing that you should try. And the third thing that you should try is removing the outliers. So winsorization is just, you need to cap the target. So if you see some values that are higher than a given threshold, you just put any higher value to that threshold, okay? Or you can also cap the error. So during prediction, during the learning phase, you have to write your own loss. And what you do is you compute the error. And for big errors, you need to cap them so that your model will not be biased towards those outliers, especially if you are using some metrics like the mean squared error, which emphasizes the importance of the outliers. So after trying the winsorization, you will have a new score that you can compare with your baseline. And the third approach is the removal of the outliers. So how can you do the removal? You just build a model and predict on the trained data set. And you have to use a cross-validation approach. It's mandatory, otherwise it's not going to work. And you will predict, and using those predictions, you will get an error, and based on this error, you will find an optimal threshold, and you will remove from your training data all the samples that have an error higher than the threshold that you have fixed. During the testing, you should not apply the winsorization on the test. But regarding the removal of the outliers, in general, you can keep the outliers in your testing data sets unless you are sure 100% that the outliers can, in no case they can be predicted. So you can remove them from your test. Also, when you see improvements, when you are doing feature engineering and you see some improvement with a new feature, how do you know that this feature is important? Because if you keep the outliers in your testing data, maybe with some luck, you are predicting a good outlier that will improve your score, but the feature by itself is meaningless. It's just some luck that happened on some outlier. So you should always check on test data with and without outliers to see if the improvement is from some kind of general pattern that your model has discovered, or it's just luck on some outliers. Okay, some additional tips that I can give you here. Always try blending your models. So what I mean here is you will, when working on tabular data, you will do a lot of feature engineering. You will sometimes end up with hundreds of features. So instead of using all those features in just one model, you can make different models with different subsets of features and try to blend together all those models. And with the feature engineering that we did in the 2 Sigma competition, we tried 5 different models, 5 same models, but with different subsets of features, and did help out a lot. Because what we have noticed, we were trying to predict in the future, so that was a time series problem, and we were trying to predict in the future on a large timestamp, and we noticed that sometimes adding one feature in our model did improve our prediction for some mounts, but decreased our score for other mounts. So each feature was not working on the whole time, on the whole unseen future. So they were working on some periods and not working on some periods. And so what we did is we clustered somehow those features into different parts. The features that were working on some periods, we put them together, and those that were working quite well on some other periods, we put them on another model, and by blending all those models, we end up with something that was quite effective on the whole period. Also, another advice that you should always try here is to try to, when using bugging, so you have the same model and you are bugging with different seeds, try to let your models overfit a little bit. By letting them overfit a little bit, sometimes the bugging will increase your score more than trying to find the best number of epochs, for example, if you are using neural networks. When you are using a lot of features, try a very small feature fraction. So this is one of the parameters of the gradient boosting decision tree. This is the number of features that will be used for each decision tree. So most of the time we are using something like 80% or 90%. But if you are using a lot of features, you should use something, or rather try something like 10% or even 5% of the features. So your trees will be really very low correlated. They will be almost independent from each other. This will increase significantly your final score. Some tips about the neural networks. Neural networks are doing feature engineering by themselves. Most of the time, when I use neural networks, I don't do any feature engineering. I just try to come up with a good architecture that is working. So when you are doing this, and in order to increase these feature engineering parts of the neural network, try to apply the embeddings also on discrete numerical features. So most of the time we only do embeddings on categorical features. This helps in feature engineering for the neural network. But doing that on discrete numerical features, you will embed those features and you will probably encode more information in those embeddings than the initial values that you are provided with. So I have noticed that those embeddings on discrete numerical features always increase my final score when using neural networks. Always do a neural network even if you are working on tabular data. They work great in ensembles and they are almost as good as gradient boosting decision trees. So when you are doing feature engineering using, for example, like GBM, and you have a lot of features that may be used to do feature engineering, it's very difficult to try all combinations with all features. You may end up with thousands and thousands of features before finding those that may help you. So one thing that I usually do, and I find it quite useful, is that I make a neural network and the gradient boosting decision tree. I have two scores, two baseline scores. I remove the same feature from both the models and I check the difference in the scores. If I see that the score of the neural network have decreased much more than the gradient boosting decision tree, then I know for sure that the neural network was doing some kind of feature engineering using that feature. So that helped me decide which feature should I focus on when doing feature engineering in gradient boosting decision trees. Another trick that may be used to improve the generalization of your models, especially when working with neural network, is to randomly replace some of the features with null values. Okay, during the training phase. So you have some generator, and for each epoch, you replace some values randomly with the null values. Most of the times it doesn't work, but sometimes it may be helpful for the generalization. Also, when working with neural networks, and this always helps, when you are working with neural networks, when you have a feature, a numerical feature with null values, always create an additional feature, which is just a Boolean feature, indicating if the corresponding value is a null or not, because you are replacing the null values into the original feature with some kind of mean or median or something like that. And you need to help your neural network by this additional information. So back to the outliers. So when you are doing the removal of the outliers from your training set, you know that later on you will do some feature engineering, and you can ask yourself, well, if I remove those outliers now, maybe feature engineering may help me later to predict those outliers correctly. So how can I decide if the removal of the outliers should be done before or after the feature engineering? So first approach, just keep the outliers until you are done with the feature engineering, so you are sure that nothing can help you in predicting those outliers. Or you can do something that I usually do, and that is what I did in the second stage of the zillow competition, is that I made a neural network, because neural networks are doing feature engineering implicitly, okay? So if I see that I'm not able to predict with my neural network, my best neural network, I'm not able to predict the outliers, and knowing that neural networks is already doing the feature engineering part, that I have some insights that probably feature engineering with gradient boosting decision tree will probably not be useful to predict those outliers. So this helped me to decide if I should remove the outliers soon or later. Okay. So I will show you here some case studies, some example of competitions, and you will see how it's maybe sometimes easy to get a gold medal or even a top 3 position. So I will start with the Mercury competition. That was a Kaggle kernel competition, so you have limited hardware, just 1 hour to run the training and the inference phase of your model. So we were provided with those features, the item description, that was the most important feature, the name, which was just a short description of the item, category, condition, shipping, and brand name. So when we started this competition, I was in a team, and we were 2 in the team, and we focused on a light GBM model because they were so good, We tried some neural networks, some rich models, and the LogicGBM was the best model that we could make. And even though it was our best model, we could not make it in the top 10 of the leaderboard. So we tried some ensembles with neural network and it didn't work. We even tried to add some embeddings coming from neural networks as new features in our LogicGBM, and it didn't work. And the running time for our LogicGBM was so high that we couldn't add any important other models because we were limited to 1 hour of training. So if something doesn't work, change your approach. We were so sad to throw that model that took us so much time to make, but we have no choice but dropping that model and come up with something new. So we tried different models that were pretty fast to train, and we used 2 neural networks and 1 rich model. So one neural network used embeddings of the words as an input, and another model just used the one-hot encoding as input. So we have a sparse input and some kind of dense input, which were our embeddings. So if you look at the architectures of our models, one model is just some dense layers, a straightforward, feed-forward neural network with a sparse input, which is our one-hot encoding. So the count vectorizer here, one of the parameters that I forget to put here was binary equal as true. So if the word is seen in the item description, it's 1, otherwise it's 0. So it's some kind of one-hot encoding. The second model was using the embedding, and the important thing that had to be done here is to use a shared embedding, because the name and the item description were using the same vocabulary. The words have the same meaning, so you have to use the same embedding for those features. And then we did something that have been used in the fast text, which is just try to capture the meaning of the sentence using an average of the different embeddings of your sentence, of your item description. And as you can see, there is no convolution here. Just averaging those embeddings and forwarding this to a dense layer was enough to have a good score. That was our second model. And the third model was a simple rich model, taking as input the description and the name features. So n-gram is equal to 1, and we made a custom n-gram with n equal to 2. And here, instead of using the classical bigram with the sliding window, we used all possible combinations of bigrams for the name, because the name was so short that we could authorize ourselves to use those kind of bigrams. And using classical bigrams and these kind of bigrams make the difference in the final ensemble. So why we went for this kind of approach? Well, we noticed that the score of each model by itself is not important. So even though our LogicGBM will have the best score, well, it was not helpful in any ensemble. And we noticed by ensembling our LogicGBM with our ridge model, the score of the ridge model by itself has no importance. So we could let our ridge overfit or not overfit. The score of the ridge model give us the same final performance. So we decided that instead of looking for the performance of each model, we should optimize for the performance of the ensemble by itself. And we tried to add models that were improving the final ensemble. Another thing that has worked is letting the models overfit a bit. That helped us in the final improvements. We also, because we have only 1 hour to run the kernels, so instead of decreasing the learning rate after each epoch, we were increasing the batch size. There is a nice paper about this that you can find on the internet, and also removing the mean from the target before the training was quite helpful. Second competition, this was a solo competition. I did just for fun because I was waiting for the zillow results. So here we have just one feature, which is you have a question and you should predict if the question is sincere or insincere. So this is an NLP problem. I started training from scratch. I have a baseline score. Sorry, it ended up. Later, when I end, you can ask questions. So training from scratch give you a baseline. It's obvious that it's not going to work because the data set was too small. So next, I used some embeddings with fine tuning. It was helpful, but not enough to get a nice ranking. So didn't work. What did work is use the embeddings, and don't fine tune your model. So the layers were not trainable for the embeddings, and this did work. So I let the model train for some epochs, and fine-tuning just the last epoch was helpful in improving the score. And then by bugging the different models with different seeds, the score improved much more. So I think that almost everyone on Kaggle used this approach. So what makes the difference in getting that gold medal? So here are the few things that I made and were quite different from other Kagglers. So because we are not changing our embeddings, the layers are not trainable. So you have to find the maximum embeddings of every word. You cannot learn embeddings for words, for new words, for rare words. So you have to find those embeddings. So what I did is an iterative pre-processing step. If I don't find the word in an embedding, I do some pre-processing and check again if its embedding is available. And I did this. So for example, tried lowercase n, uppercase n, remove the accents, etc., and check again if the embedding is available. And the last pre-processing step is the stemming. This is the last thing that I do. And if I don't find the stem of the word in the embedding, then I consider the word as a rare word. And this was the most important tips that I have used in the pre-processing, and it improved significantly the performance of the model. The next thing that I did is, because the embeddings of the rare words are not available, and I'm not going to learn them because my layers are not trainable. So I cannot use them when I will do some global averaging or global maxing. So I always multiply those embeddings by 0, otherwise I will use some random values that will not change during the training. This was quite helpful into improving the score. And later, I didn't use the global averaging because I have a lot of zeros embedded in my inputs because of the padding and because of the rare words that I multiply by 0. So I have a lot of zeros, and averaging would not work. So what I did is, instead of averaging, I just sum up the values of the embeddings. Then I apply some batch normalization. And here is my architecture. That's the full network, and it's pretty straightforward to understand. So I have an input which is the question by itself, and another input which is just a binary indicator telling me if the word is in the embedding or if the word is a rare word which is not in the embedding. Then I use the glove embedding here. So I don't initialize my embeddings with some randomness, but I use a transfer learning to initialize my embeddings, and then I multiply, this is the tricky part here, I multiply my embeddings with the mask. So rare words will be multiplied by 0, the embeddings will be equal to 0, otherwise I will use the transfer learning. And then there are two parts here. This is the fast text approach. You just try to capture some kind of meaning of the sentence. So usually what we do is average all the embeddings, but the average here was not working because I mostly have zeros in my sentences. So what I did is just sum the embeddings, apply batch normalization on it. My second part of the network is just use an LSTM or on my input and apply a global max pooling, and again I cannot use the global average pooling, I just use the sum. Concatenate everything and straightforward to a neural network. As you can see, quite simple, but those three little tricks made the difference. And I end up just in a few days of work in the 14th place. I was ranked 14 and I got a gold medal, which something as simple as that. Oh, sorry. The last competition I will talk about is a recommendation system for music. So the problem is the following. We have a user who is listening to some song at some time stamp T1, and we want to predict if the same user will re-listen to the same song at some time stamp T2. And T2 minus T1 is less than 1 month. So we are trying to predict if there is any re-listening of the song for each user. We have some statistics here, but the important thing to note here is that the cold start problem was extreme here. We have almost 26% of new songs in the testing data, so we have to deal with this cold start problem. Those are the features that were provided, and the most important features were the user ID, the song ID, the source type, and the artist name. So those are the features I will focus on. So what we did, so we used here the light GBM model. So we computed different statistical features based on the user, the song, and the artist, and we noticed that using statistics, using the target was not working. And you will see next. It's over? 2 minutes? Okay. So the dataset didn't include any timestamp or session information, but we noticed by doing some analysis that it was chronologically ordered. So what we did is we approximate sessions of the users by using some little trick. Just look at the indexes, shift it by 1, try to take the difference. If the values are small, this means that those samples are in the same session. If the value is high, this means that it's happening in some other sessions. This is the first trick that we used. Second one, we noticed that using the user and the song ID did help in our cross-validation, but the model was really overfitting on those. And as I said before, when you have features and your model is overfitting on it, either you remove them or you apply some transformation. Because they were helping, we apply some transformation and we come up with different SVD embeddings for those features. We also noticed this is how the mean target was evolving, and as you can see, there is a nice trend here, and we tried to capture that trend. So we made 2 linear regression models. We trained them on the sessions, and we extract those features from the linear models, and we added those as features in our light GBM. Also, in order, and this is my last slide, in order to somehow overcome the cold start problem of the songs, what we did is we create an adjacency matrix of the last songs that each user had listened to. And so we took the last 30 songs of each user and we put a 1 in our matrix if two songs are in those last songs, otherwise it's a 0. And then we applied an SVD on that and used the embedding as inputs. It did help in to overcome the cold start problem, because if you have some new songs that have never been seen before, it will be related to other songs that have been listened by the users, and the embedding will capture this kind of information. Okay, and we end up again like we did in the 2 Sigma approach by using 5 models, 5 light GBM models, and we just use different subsets of features for each model, and then we blend together all the models. Thank you for your attention. Any questions? I don't know if it's working. I don't know. Is it working?
Is it working? Oh yeah, I can hear it at least. Do you recommend any good like books or learning materials? What like learning materials or books do you recommend for learning more about
Materials
this?
that I recommend?
Yeah.
Okay. So I'm asked to give some recommendation about good materials. I think that Kaggle kernels and Kaggle discussion are the best materials. When I started doing data science, I learned everything from the Kaggle platform. I didn't start by reading papers or reading books. I start directly doing competitions and reading discussion and kernels. Later on, to have better understanding, I start reading papers, scientific papers, to get more insights about why things are working or not. So, you have a question, I think?
No, I had one, but I forgot.
Okay.
Can you talk a little bit more about what is the use of fitting base models, for example, linear or logistic regression, and using them as input to more sophisticated models?
Okay. Sit down. One question. So the question is, in the last example that I show you, why did I use the linear regression models and why I use them in my light GBM model? So because we had that trend of the meaning of the target that was clearly decreasing in time, I should capture that trend. And decision trees based models cannot capture this kind of trends. So the idea is to use a linear model to capture the trend, and from those models, those linear models, I extracted as features the slope for each user. I captured the slope and the difference between the starting and the last value predicted by my linear regression model. So this somehow is capturing the dynamic change of the user behavior that I cannot capture with decision tree models.